Now let us start looking into block diagram of digital filters. We will be discussing about the block diagram of both IIR and FIR filters as a part of this section. Before going into the block diagram of the digital filters, we will look into some of the block diagram symbols. Let us consider the adder, which is a basic element of a block diagram, which takes the inputs as x1 of n and x2 of n. Then the output is given as x1 of n plus x2 of n. Similarly, there is a scalar that is possible. If the input of the scalar is x of n, the output is given as a into x of n, and the same is as shown. There is a delay element that is also needed as a part of the block diagram, which is denoted as shown in the figure. It takes the input as x of n and the output of the same is x of n minus 1. The three symbols that we discussed just now are basic elements of the block diagrams. Let it be FIR or IIR filter, these symbols are very much used. Now let us start looking into the block diagrams of IIR filter. As a part of the block diagram realization of IIR filters, let us consider a generic LCCDE which is given as y of n is equal to sigma k equal to 1 to n ak multiplied by y of n minus k plus sigma k equal to 0 to m bk x of n minus k. The system function of the above LCCDE can be obtained by taking Z transform on both sides, which is given as h of z is equal to y of z divided by x of z is equal to sigma k equal to 0 to m bk multiplied by z power minus k divided by 1 minus sigma k equal to 1 to n ak z power minus k. Before looking into the different implementations of block diagrams of IR filters, one point that needs to be clearly mentioned is that we will be looking into the realization by using examples. Of course, the same can be generalized for any LCCDE or system function. Let us consider a system function which is given as h of z is equal to 1 minus 2z inverse, say 1 plus 2z inverse plus z power minus 2 divided by 1 minus 1 by 2 z inverse minus 1 by 3 z power minus 2. This is equal to y of z divided by x of z. Upon simplifying this system function with y of z terms on left hand side and x of z terms on right hand side, and after taking inverse z transform, we get the LCCDE of the system as y of n minus 1 by 2 y of n minus 1 minus 1 by 3 y of n minus 2 is equal to x of n plus 2 into x of n minus 1 plus x of n minus 2. So let us look into the direct form realization of this system function. Suppose the input to the filter implementation is x of n. We see that we need to realize the terms x of n, x of n minus 1, and x of n minus 2. So we need to add delay elements as shown in the figure, which are mainly to produce x of n minus 1 and x of n minus 2. We also see that we need to realize the sum x of n plus 2 into x of n minus 1 plus x of n minus 2. So upon weighting x of n minus 1 by 2, that is mainly for the second term on right hand side, that is marked, and by weighting x of n minus 2 by 1 and by weighting x of n by 1, we need to add the different terms to get the intermediate output, which corresponds to the term on right hand side. Also please note that the filter structure that we realized so far corresponds to 1 by 1 minus 1 by 2 z inverse minus 1 by 3 z power minus 2. So this corresponds to the denominator polynomial, say 1 by b of z. Now we also see that to the term on right hand side, we need to add 1 by 2 y of n minus 1 and 1 by 3 y of n minus 2. If we assume the output as y of n as shown, we need to add delay elements z inverse to get y of n minus 1 and y of n minus 2. Also by weighting y of n minus 1 and y of n minus 2 by 1 by 2 and 1 by 3, we see that the filter structure that can be realized is as shown. And also the filter structure on right hand side that is implemented just now corresponds to the numerator polynomial a of z, which can be written as 1 plus 2 z inverse plus z power minus 2. Please note that the implementation that we have done just now is also called as or is called as direct form 1 implementation. We are realizing these filter structures for a LTI system of system function h of z that is equal to a of z divided by b of z. Currently, we realize the filter structure as 1 by b of z multiplied by a of z. As the system is LTI, the same can be realized as a of z multiplied by 1 by b of z. That is, by swapping the right hand side structure and the left hand side structure, we can still realize a block diagram that is corresponding to h of z. So the swapping of a of z and 1 by b of z results in the form which is called as direct form 2. Please note that the direct form 1 and the direct form 2 are equivalent and realize the same h of z, except that a of z and 1 by b of z are swapped. Also please note that once the direct form 2 is obtained, we can combine the delay elements as shown in the figure, mainly to get another form of direct form 2 implementation. So from this, we can write the filter structure as shown, or we can obtain the filter structure as shown, where the weights can be written as 1 by 2, 1 by 3, 1, 2, and 1 as shown. Here it has happened that the order of A of Z is equal to the order of B of Z. Please note that we can realize the similar filter structures even if order of A of Z is not equal to order of B of Z. So for a given IR filter, we have seen how a direct form 1 implementation can be obtained. We have also mentioned that direct form 2 implementation can be obtained by swapping or by making minor modifications related to swapping in direct form 1 implementation. We have also seen that the delay elements can be combined in direct form 2 implementation so as to get another or alternative form of direct form 2 implementation. Now, let us look into another form of implementation of IR filters, that is called cascade implementation. As the name says, in cascade implementation, we realize the filter structure as cascade connection of direct form realization. So let us consider an example in which the system function of a LTI system is given as h of z is equal to 1 minus 1 plus 2z inverse divided by 1 plus 3z inverse multiplied by 1 plus half z inverse multiplied by 1 plus 1 by 3 z inverse. From this filter given, we see that h of z can be realized as cascade connection of filter 1, that is marked as shown, and filter 2, which is also as shown. From this we see that the filter can be realized as accepting an input of x of n. Suppose there is a delay element z inverse, then the weighting factors can be mentioned as -3. Similarly, the weighting factor here is 2. Please note that we got an implementation of F1 here, which is direct form 2. Now we realize F2 also by using direct form 2 implementation. And the same can be same can be drawn as minus, minus 1 by 3 and with a weight of 1 by 2 as shown. So the output of the filter is y of n. So here in the direct form 2 implementation, the weights on right hand side correspond to the numerator and the weights on left hand side correspond to the denominator. However, we need to take the negative of the coefficients for realizing the implementation. Similarly, for the F2 also, we see a weight of 1 by 2 on right hand side and we see a weight of minus 1 by 3 on left hand side. From this we see that given any filter h of z, if both numerator and denominator polynomials or either of them can be factorized into product of polynomials, then we can realize the cascade connection of direct form implementations. Now let us look into another form of implementation, that is called parallel implementation. In this, the filter structure is realized as sum of implementations, where each implementation can be a direct form implementation or a cascade implementation. Let us consider an example in which the system function of a LTI system is given as 1 plus Z inverse plus 1 plus Z inverse divided by 1 minus Z inverse plus Z power minus 2. Here we can realize h of z as addition of a direct form implementation f3 and f1 which is 1 and f2 which is z inverse. From this we see that the parallel implementation can be drawn as shown. The first branch corresponds to the weight 1, the second branch corresponds to the weight z inverse, the outputs of which are added to get the y of n. Now we realize F3 by using direct form implementation as shown. Here there will be two delay elements Z inverse, and as already mentioned the coefficients on right hand side correspond to the numerator, so there is a weight of 1, and the coefficients on left hand side correspond to the negative value of denominator, so which would be 1 and minus 1. So now we realize the direct form implementation of filter F3 here. So let the input be X of n. From this we see that given any digital filter, we can realize the implementation by using either direct form 1 or direct form 2 or alternate direct form 2 or cascade implementation or parallel implementation. So using either of these, we can realize the filter structure of a IIR filter. Now let us look into digital filter structure realizations of FIR filter. Before going ahead with the same, let us assume that there is a signal X of n which is convolved with H of n to get an output of Y of n. This is considered as a FIR filter, which can be written as sigma k equal to 0 to n, sigma k equal to 0 to m h of m multiplied by x of n minus m. So the direct form implementation of the same can be as shown in the figure. Let us consider an input of x of n. Now, due to the introduction of delay elements, we see that the output after each stage would be x of n minus 1, x of n minus 2, and so on till x of n minus m. Now, these intermediate outputs we got, that is delayed version of x of n, are weighted by h of k and then added to get output of y of n, which is equal to sigma k equal to 0 to m h of m multiplied by x of n minus m. Sorry, let this be m. Let this also be m. So the output at this point is equal to h of 0 into x of n. The output at this point is equal to h of 1 multiplied by x of n minus 1. The output at this point is equal to h of m multiplied by x of n minus 1. All these intermediate outputs are added to get y of n. So this is called the direct form implementation of a FIR filter. It is also, see, here we have taken x of n, delayed it first, and then weighted by h of n to get y of n. It is also possible to get a transposition of above network in which the weights are performed first and the delays are performed later. Suppose the weights performed are h of m, h of m minus 1, and so on till h of 0. Now, after performing the weights on x of n, the delays are performed at different quantums, that is z inverse, z power minus 1, and so on to get the output y of n. Please note that the realization that we got now is the transposition of the direct form implementation that we have already discussed. Now, let us look into the cascade implementation of FIR filters. Please note that in case of FIR filters, we are discussing about the filter structure realizations using a generic form. Of course, the examples will be covered subsequently. Let us consider h of z, which can be written as 1 plus z inverse plus z power minus 2 multiplied by 1 plus half z inverse plus 1 by 3 z power minus 2. From this, we see that the FIR filter can be realized as cascade connection of two FIR filters, and each of these FIR filters, that is F1 and F2, can be realized through direct form implementation as shown. Let the input be x of n, which is delayed by z inverse twice, and the output, that is x of n minus 1 and x of n minus 2, are weighted by 1 to get a intermediate output. The realization that we have seen till now is of that of f1, which is of direct form. Now we realize filter 2 using the delay elements z inverse, and the outputs obtained after the delay elements are weighted by 1 by 2 and 1 by 3. And the implementation that we have done now corresponds to filter 2. So from this we see that in case of filter 1, the coefficient of z inverse is 1, which corresponds to the point 1 we marked, and the coefficient of z power minus 2 is also 1, which corresponds to the one we marked. Similarly, in case of f2, the coefficient of z inverse is half, which is as shown, and the coefficient of z power minus 2 is 1 by 3, which is also as shown. So here we see that we got the cascade connection of FIR filters using the direct form implementations as shown. Till now we discussed into different realizations of FIR and IIR filters. Now we will look into different filter structures or block diagrams possible for a linear phase FIR system. Let us consider a linear phase FIR system which satisfies the symmetry conditions as shown, that is h of n is equal to h of capital M minus n where n runs from 0, 1, and so on till m. Another form of linear phase FIR filter possible is h of n is equal to minus h of m minus n, where n runs from 0, 1, and so on till m. So here we will be discussing about linear phase FIR systems. In case of linear phase FIR systems, the impulse response can satisfy the conditions given, where m can be even or odd. So depending on m, that is even or odd, and the sign, the linear phase FIR filters linear phase FIR filter can be classified as type 1 or 2 or 3 or 4. So depending on the nature of m, that is even or odd, and depending on the sign, that is plus or minus, we can realize the filters. We can classify the linear phase FIR filter as type 1 or 2 or 3 or 4. Now let us consider a case out of the two linear phase FIR systems that we discussed before, where h of n is equal to h of plus or minus h of m minus n, where m is even. In this case, the filter can be realized as shown, where the branches that we are marking now correspond to delay elements. So, because of which, for an input output x of n, the output at the end of each z inverse will be x of n, x of n minus 1, x of n minus 2, and so on. Now, these outputs are weighted by h of 0, h of 1, h of m by 2 to get an output of y of n. Please note that here the signals at different points are marked as shown, that is x of n minus 1, x of n minus 2, and so on, x of n minus m by 2, and x of n minus m. Now, these signals are weighted by plus or minus 1. This is because depending on the sign, that is, if it is positive sign, we have to choose positive sign for this branch. If it is negative sign in the impulse response of equation that we have given before, we have to consider negative sign here. Also, please note that the filter structure that we realized just now is equivalent to above equation, and also this is called direct form implementation, where m is even integer. So the structure that we realized just now is specific to the case of m being a even integer. When m is odd integer, the structure can be realized as shown, but as m is odd, the structure gets modified slightly as shown. Here we are adding a delay z inverse on the right hand side, where the delay z inverse was not present previously. This has come into picture as m is an odd integer. Now the different signals are weighted by h of 0, sorry, h of 1, and so on till h of m minus 1 by 2. Now these signals are added to get an output of y of n. Please note that similar to before, there is a plus or minus sign here which correspond to the sign present inherently in the impulse response h of n. Also, the structure that we realized just now corresponds to a direct form implementation of FIR linear phase system where m is odd integer. So now we discussed about linear phase FIR filters where m is even or odd. Depending on the case, we realized two direct form to implementations. Now let us solve some of the problems as related to the same. Let us consider a filter structure which is given as shown in the figure. It takes an input of x of n and gives an output of y of n. There is a delay element z inverse present. Please note that the delayed signals are weighted by A1 and A2 as shown in the figure. Now it is given that the structure shown corresponds to a system function of 1 minus z inverse divided by 1 plus z inverse. We need to find the values of A1 and A2 from the figure given. We know that h of z is equal to y of z divided by x of z. This is equal to 1 minus z inverse divided by 1 plus z inverse. This can be simplified as y of z plus z inverse y of z is equal to x of z minus z inverse x of z. Assuming that the system is causal, we take inverse z transform on both sides to get an LCCDE of y of n is equal to y of minus y of n minus 1 plus x of n minus x of n minus 1. Now we see that from the figure the intermediate output can be written as a of n, where a of n is equal to x of n plus a1 into x of n minus 1, and the output y of n can be written as a of n plus a2 into y of n minus 1. So upon simplifying we get y of n is equal to x of n plus a1 x of n minus 1 plus a2 y of n minus 1. Upon comparing the LCCDE that we got from the system function with the LCCDE that we got from the filter structure, we get that a1 is equal to minus 1 and a2 is equal to minus 1. So here we have got the LCCDE corresponding to the system function. Then we got the LCCDE that corresponds to the filter structure. Based on that, we found that A1 is equal to minus 1 and A2 is equal to minus 1. So from this we see that given any arbitrary filter structure, we can get the LCCDE from the system function and we can get the LCCDE from filter structure and compare these two to get the required coefficients or values. So using this mechanism, we can get the required values in the filter structure or in the LCCDE by comparing both of them.